Hello everyone, good morning everyone. So this is QIP virtual session on Friday. My name is Keisuke Fuji at Osaka University, chairing this session. This session is invited talk given by Pavel Panteleev. Title of his talk is Good Quantum Low Density Parity Check Codes and Their Classical Relatives. So presentation time is 60 minutes, including Q&A. If you have any question, please use chat box. So, okay, then Pavel, over to you.
Okay, thank you. Thank you for a very kind introduction. So as it follows from the title, the talk will be devoted to low density parity check codes, and we can see the both quantum codes that are relevant to this conference, and I say something about also their classical counterparts and some result that is also related with these quantum low density parity check codes. This is a joint work with Gleb Kalachev. So let us start. Okay. Okay, first of all, let me remind you the definition. So I suppose in QIP many already know what LDPC codes are, but let me just remind. So a classical LDPC code is just a linear code. It's a linear code, so it is defined by a set of linear equations, and this set of linear equations are usually represented by the parity check matrix. So we have, as for any linear code, so we have standard parameters like the length of the code, so the number of bits. We have the dimension of the code, the number of the useful bits, and we also have a very important parameter that is called minimal distance. So it says you how many errors your classical code can correct. And this, so I didn't say what is classical LDPC code. So LDPC code means that this parity check matrix that I mentioned, this parity check matrix H is a low density. And by low density, usually different people mean different things. But in this talk, we assume that we have an infinite family of codes, and for this infinite family of codes, we have some universal constant W, and all rows and columns of all the parity check matrices in these codes are upper bounded by this constant. We usually represent classical DPC codes by Tanner graphs. So these are special bipartite graphs where I have two parts. So first part corresponds to the bits. So this first part of nodes corresponds to bits, and the second part of nodes corresponds to checks. And each check is just one row from this parity check matrix. So, for example, if you have here some 0 1s, so you can look at the check, you sum up the bits that connected to these checks, you sum up them modulo 2, and if you obtain 0, then you say that this check is satisfied. If you obtain non-zero, then this check is not satisfied. So you can also consider this Tanner graph as some constraint graph. Yes, you have bits and you have a number of local constraints. And since we consider LDPC code, so each constraint, so each bit participate in just constant number of checks, and in each check we have only constant number of bits. Okay, so these codes were introduced by Robert Gallagher in the 60s, and they nowadays they are used everywhere, including SSD, Wi-Fi, and 5G, and some other communication standards. And what is known about classical LDPC codes? It is known that there exist explicit families of asymptotically good LDPC codes. And by asymptotically good or just good families of codes, I mean that these parameters, the number of useful bits and the minimum distance, so they grow linearly with the size of the code. And actually, the first explicit construction with a linear time decoding and encoding was obtained much later in 90s by Sipser and Spielman. But this conference is dedicated to quantum. Of course, we are interested in quantum codes. And so I assume that everyone here know what is quantum CSS code is. And so by quantum LDPC code, I mean quantum CSS code. And as you know, a CSS code is usually defined by a couple of classical linear codes. And this couple of linear codes are defined by the corresponding parity check matrices HX and HZ, which roughly speaking corresponds to the X errors and Z errors, poly errors that occur in your quantum code. And so you also still have these standard parameters, the length of the code and the dimension of the code K and the minimal distance. And actually the meaning of these three parameters is approximately the same. So they're just analogs for the classical codes. And but the formal definition is slightly different. So there is a difference because in quantum codes we have some of the errors, so we do not need to correct them. So these errors corresponds to stabilizers, and that is why the minimal distance is defined in a slightly different way. So what is quantum LDPC code? So quantum LDPC code, as I said, say CSS code is defined by a pair of parity check matrices, and you can represent this pair of parity check matrices by also by a Tanner graph. But in this case, you have three parts. So the middle part corresponds to qubits, and you have also two parts that corresponds to X checks and Z checks. So X checks, they are responsible for X errors, and Z checks, they responsible for Z errors. And the famous example of quantum LDPC code is, of course, a Kitaev's toric code, which I assume many of you already know. And what is quantum LDPC code? As in the classical case, so we say that this code is LDPC if all qubits participate in the constant number of checks, either X or Z, and in each check we have only constant number of qubits. And this is, by the way, this is much more important for quantum codes than for classical codes. I mean, this constraint, because in quantum code we do not want to disturb qubits too much, because each check is actually some measurement that we perform on the qubits, and we want to measure as small as possible. Okay, and as you know, there are a lot of quantum LDPC codes with suboptimal parameters, such as surface codes, color codes, hypergraph product codes, and a major open question, which is not open. So it's called QLDPC conjecture, and it asks whether there exists good families of quantum LDPC codes. Okay. Let me first briefly describe the history of this question. So I already mentioned this toric code that was introduced by Kitaev in 1996, and after that it was generalized in many ways, and some similar constructions were proposed, for example, surface code and color codes that are considered now the most practical codes for quantum computers. And so this actually, so I forgot to say that these codes, the historic codes and surface and color codes, they have minimum distance that grows only as a square root of n. And actually, this was slightly improved by Friedman, Mayer, and Lua in 2002, and they use some quite sophisticated construction, topological constructions that involved fiber bundles, and they managed to slightly outperform this bound, this distant bound. However, I should say that all the codes that I mentioned before, they have only constant number of logical qubits. And the problem with number, and of course, if we want to our efficiency of our quantum computer to be good, so we want the number of logical qubits to, that grows linearly with the with the length of the code. And this was achieved by the famous hypergraph product construction by Tillich and Zemmer. And then it followed by a number also very great results by Brawi and Hastings and other guys. And for example, small set flip decoder was introduced that can efficiently decode these codes. And it was shown that it was even shown using these constructions that constant overhead fault tolerant protocol can be implemented using the result of Gottesman. And actually, from this time, so there was also some interesting construction between 2009 and 2020, but in terms of the minimum distance, there was no progress. And so the first, so in the papers, the first papers that break these previous records appeared only in 2020. So first it was papers that considered high dimensional expanders, and they show that it is possible to go slightly further, so you can improve these logarithmic factors. But then after that, there was a breakthrough by Hastings, Haag, and O'Donnell, and what they propose, they propose some very interesting constructions that is based on fiber bundles, and they also propose some general product that they call twisted product. And the codes that they obtain, they surpass this square root barrier. And this was a really great achievement, because before this, so I suspect that many people even considered that you cannot go far beyond the square root of n. And so maybe there should be some even fundamental limit. But they showed that there are no such limits, and hence, of course, if you have 3, 5, maybe you can have 5, 6, or some arbitrary values close to 1. And after that, so in our joint work with Gleb, Kalachev, so we show that this is indeed possible using a similar construction. And in this paper, we also introduced some general product that we called lifted product. And we also consider two cases. So the cases lifted product of 2 codes and lifted products of 2 chain complexes. And they of course are relevant. So the lifted product of chain complexes is just a special case of tensor product. Standard idea from homological algebra, it's a tensor product over some group algebra. And we also used in our construction Sipser-Spielmann expander codes to obtain this bound. So after that, so appeared a very interesting paper by Brookman and Eberhard. And by the way, so it appeared just shortly afterwards our paper. And in fact, many of the results in their papers were obtained independently, and they actually proposed very similar construction. So it is still a tensor product over group algebra, but they considered more general case from the very beginning. And what is even much more important, they also connected this tensor product over group algebra with operation in topology. So they gave a geometrical interpretation of this operation, and they showed that it corresponds to the balanced product of topological spaces. And this was a really great achievement. And they also, of course, obtained some nice constructions of codes, but it didn't break any records. But what is important, they proposed also some explicit constructions. So these previous two constructions were not explicit, and they proposed a way to construct these codes explicitly and using Kelly graphs and using LPS expanders. Okay. It is also interesting to know that actually these three main results that were obtained, they are just instances of lifted, so some preliminary version of lifted product that we introduced in 2019. So we called it GHP codes that time. So when we showed in this paper that using some special decoder called BPOSD, that these codes this class of codes can be decoded, efficiently decoded on depolarizing noise, and you can even beat the surface code, and you can even beat it if it is decoded using optimal decoder, maximum likelihood decoder. So, so in some sense, so for this class of codes, so we formally proved they have these distances. So we have some practical achievements that shows that they work in practice. And what is also interesting, that this class of codes also can be considered as a special case of hyperbicycle codes introduced by Kovalev and Pritko in 2012. And so it's almost 10 years ago. And all these codes actually also corresponds to Kovalev-Pritko codes. And hence we starting from 2012, we already have a class of codes that have almost linear minimum distance. We just didn't know how particularly constructed. What is also interesting that quite recently our construction of almost linear minimum distance codes was shown. So in our construction we use random lifts, but it was shown that in fact you can de-randomize this construction and use explicit lifts. Okay, so as I said in this talk, I also want to mention about some relevant results. So that's at first glance looked quite not related with the quantum codes, but in fact it is really well related with it. So this is a result concerning the local testable codes. So now what is local testable code? So local testable code is just a special type of LDPC code. So usually they are LDPC, but not necessary. And a code is called WS locally testable if it has parity check matrix H with bounded weight. And for each vector x, we have the following inequality. And here D means the distance from some bit string to the code C. So actually, so let me explain what this means. So this means that if we have a code and if we have some vector, for example, corrupted code word, then we can estimate the distance to the code just by looking at the syndrome. So by syndrome, I mean, if we multiply by the parity check matrix, we obtain some vector hx, and this vector is called syndrome. And so by looking at the syndrome, so you can estimate the distance to the code. And actually for LDPC code, so it means that this distance is just up to some constant factors is proportional to the weight of the syndrome. So not every code is locally testable. For example, if you consider, for example, repetition code, standard repetition code, it is not locally testable. It can be easily shown. But what is interesting that all known locally testable codes are usually very, very redundant. And by redundant, I mean that the number of checks they have is much more than that is really needed. For example, the famous one of the first locally testable code is Hadamard code, and it is defined as so you can see the all linear functions on n variables, on n binary variables, and you apply these functions. You calculate this function on all possible values, and this way you obtain a linear code. It has length equal to the power of n. But how you can check that some particular function is linear? Yes, you can just use this simple check. So every linear function should satisfy this check. Yes, and you can see that the number of checks that you have. So you can choose any A and B, and you have some check. And this check, so it just uses 3 bits. So is this bit, and this bit. And so you can see that you can choose A and B so you can choose A and B, this pair of A and B, 2 to the power of 2 to the n number of so you can choose this A and B in much more ways than you have the length of the code. So the length of the code is to the power of n, and the number of checks that corresponds to these checks is roughly a square of it. So you have much more checks than the bits, and this means that these checks are redundant. And if they are redundant, this means that you can also have checks on checks. So you can have meta checks. And this, if you look at this really reminds you about quantum LDPC codes, because in quantum LDPC codes, we have 3 levels. So we have in the intermediate level, we have qubits, and we have X check and Z checks. But here, so we can see that we also have 3 layers, but we have different interpretation of these layers. Okay. And what was known about locally testable code? It was known that they are used in the PCP theorem, famous PCP theorem. And actually, I'm not aware of any practical applications of locally testable codes, but at least they're very interesting from theoretical point of view. And compared to quantum LDPC codes, locally testable codes with almost optimum parameters were known for a long time. So almost from the very beginning of this type of codes, people knew how to construct codes with almost optimal parameters. By optimal parameters, I mean constant number of information bits and constant linear number of information bits and linear number of for the distance. And major open problem as for the quantum codes, it was called C3 LTC conjecture, is whether there are good families of codes. So there are almost good, but other good families of locally testable codes. And quite surprisingly, it is possible to solve both problems using approximately the same construction. And so the main results of our paper are the following. So first, we show that for every number which is arbitrarily close to 1/2, and every finite field, even finite field of odd characteristics, it is possible to find universal constants S and W such that there exists an explicit family of locally testable codes. And another theorem says that for any rate, for any number R arbitrarily close to 1 in this case, it is also possible to construct an explicit family of quantum LDPC codes. And I should also say that this result regarding locally testable codes was also independently obtained by Dinur and et al. And they managed to construct codes which are arbitrarily close to 1 with a rate which is arbitrarily close to 1. So in our case, it is only 1/2. I should also say about very recent results that appeared just, some of them just appeared just several days ago. And this is a new construction of Lin and Shea that appeared quite recently. And so the idea is very similar to the lifted product. So, so it considers a lifted product of for two codes A and B defined by parity-check matrices A and B, and if these parity-check matrices A and B are adjacency matrices of bipartite lossless expanders, then you can obtain very interesting codes. And what means by what I mean by lossless expander? By lossless expander, I just special kinds of bipartite graphs where so in bipartite graph you have two parts, and if, for example, in each vertex in this part have degree D, then in lossless expander, so you consider some small set, some sufficiently small set, and you consider the number of vertices in the different part. And for lossless expander, so roughly speaking, the number of neighboring vertices is approximately the same. So it's maybe 99% of the maximum possible value. And of course, the maximum possible value is D multiplied by the size of S. And this is what is called a lossless expander, and it can be one-sided if you have only this property from left to right, and it can be also two-sided if you have this property from left to right and from right to left. And what was shown, it was shown that it is possible to use this construction to, if you are able to construct one-sided lossless expander, then it was shown also that they do exist. And then it is possible also to prove the theorem 1, which is really cool. And the proof is, I should say, is much easier than that we have for our construction. And what was also shown, and this is a very new result, and that it is if you can construct two-sided lossless expander, which right now it is not known whether it exists or not. But if one can construct such an object, then you can obtain not only a good quantum LDPC codes, you can also obtain a linear time decoder, which is really cool. And I should also say another type of construction, which is also somewhat similar to the ones that we considered by Anthony Levier and Zemmour. And it was called quantum tenor codes, and in fact it indeed looks like a generalization of classical tenor codes, and it also can be used to obtain this theorem too. So just to summarize, so right now we have quite a number of constructions, and if you even don't believe in our construction, so you can believe in this maybe much more simple. Some of these constructions are much more simple than ours. Okay. In order to describe our construction, let me describe say about something about chain complexes. So it's some algebraic idea. So it's a collection of vector space. So what is a chain complex? So chain complex actually it's a modern view of LDPC codes, including classical and quantum codes. So a chain complex is just a bunch of vector spaces, and you also have a linear map, a bunch of linear maps between these vector spaces, and you have this special property. If you apply two linear maps, you always obtain 0. And this property implies that you can define the boundary, which is the image of this this map, and you can also define so-called cycles, which are kernel of this map. And since you have this property, you have that this image is subset of this kernel. And this is, I should say, this is very similar to the CSS construction. If you remember, one of the possible way to define a CSS construction is just to construct two codes. Yes, the code that corresponds to degenerate errors, yes, and the code that corresponds to all the code words. And you can define for each chain complex, you can define is homology group, it's just this quotient. And you can also consider this homology group as a metric space. And this way you have this connection with the quantum code. And what is the distance we use for the homology group? So homology group is a bunch of factor spaces, and the distance between two homology classes is just the distance, minimal Hamming distance between different bit strings. So in this sense, so this homology group just comes with a quotient Hamming matrix. And geometrically, it corresponds to, if we consider, for example, toric code or some other similar constructions. So it corresponds to the systolic distance. So it corresponds to the weight of non-contractible loop. You can also consider some dual notion where you just reverse all errors and you just add call to each definition, and you also have the distance for this co-chain complex. And this duality actually it corresponds to the fact that for quantum codes we have X and Z errors, and they are also in some sense are dual, as you know, and actually this duality corresponds to this duality of chain complexes. Okay, but how we view LDPC codes as chain complexes? We view them as For example, classical LDPC code is just a two-term chain complexes. You have first term that corresponds to bits, and you have second term that corresponds to checks. And this boundary map is just a map. This is just a parity check matrix. And the distance is just the standard distance, which in fact corresponds to this homological distance. Because in this case, we do not have so we do not have a term here. So it means that here we have a zero term, and so by definition we consider that we assume that boundaries, the space of boundaries is zero. Then in this case, so this two-term chain complex, its minimum distance corresponds to this standard homological distance. And for quantum codes, for quantum LDPC codes, we have a three-term complex. So we have first term that corresponds to Z checks, second, so intermediate level to qubits, and the last level to X check. And if you can consider dual complex, so you obtain a dual quantum code where X and Z checks just play different roles. So you just exchange the roles of X and Z. And in this way, you obtain a dual chain complex. And you also have two minimal distances that corresponds to homological and co-homological distance, or systolic or co-systolic distance, if you prefer. Okay. So let me summarize. So we have classical locally testable codes that have three levels, as I said, and we have quantum LDPC codes that also have three levels. And actually, the main idea of our paper is to construct some object that can be used for both of these tasks. And in fact, this object exists. And using this object, which I will describe in the next slides. So we can consider the same object, but we can interpret it in a different way. So in the first interpretation, so we interpret this level as bits, and this as checks, and this is a MITI checks. And in this way, we obtain locally testable codes, and it corresponds to the code that corresponds to the second homology. And you can also interpret it differently, and this way we obtain quantum LDPC code, and the qubits in this case corresponds to the first homology. And what is interesting, so this idea can be also generalized to, for example, to 5 layers. And so, for example, you can find this idea in the brilliant paper of Earl Campbell. He considered it for single-shot decoding, but so I assume that this kind of 5-term complex can be used also to prove some other interesting conjectures. For example, quantum LTC conjecture, which is the analog. So quantum LTC is just a quantum analog of a local testable code. So this is just a code. This is just a quantum code where this code that corresponds to X check is locally testable, and this code that corresponds to Z checks is also locally testable. And the existence of these codes is still open, and if they exist, then this also has some interesting consequences, like the famous NLTS conjecture by Hastings and Friedman. And my hope that these general constructions, these general ideas can be used also to tackle this conjecture. Okay, let me describe the idea of the lifted product. So the idea of the lifted product, it's an idea that we used in our construction. So as the idea of the lifted product, so as it follows from its name, it contains two components, lift and product. So let me first define what is lift. So let us define the lift for graphs and codes. So for example, we have some small graph and consider some edge in this graph. And assume that we have also some group G, and we assign to each edge a group element. This is in different communities, it is called by different names, but historic name for this is a voltage assignment. And after we do this, we can obtain what is called a G-lift. So a G-lift is just larger graph, which is obtained from this small graph. And so it is obtained in the following way. So we replace each vertex by G elements by the number of elements is equal to the size of G. And we also replace each edge by size of G number of edges, and we connect these edges corresponding to this element, this voltage. This sometimes it is also called shift. This shift element, and this way obtain G-lifted graph. For example, we can consider such small graph, and we can consider this cyclic group that consists of 3 elements. And after G-lift, we obtain this graph. Yes, here we have, for example, here we have shift value equal to 1. It means that this zero variable is connected to 1, 1 is connected to 2, and 2 is connected to 0. So and each group of bits that corresponds to 1 bit is called a fiber, and each fiber it can be identified with a group. What is really interesting that you can also apply this to codes, not only to graphs. Since each LDPC code is described by some graph, so we can obtain, for example, starting by a small LDPC code, we can obtain a large LDPC code. And we can also use this G-lifted product idea. What is known about G-lifted graphs? It is known that it is actually the same as the graph with a free action of group G on vertices and edges that also, of course, respect the adjacency of the graph. And G-lifted code, it is known that it is the same as code with some symmetry. So with a free action of group G on the bit position. And in the case of cyclic groups, such code are usually called quasi-cyclic codes. Okay. I should say that almost all classical LDPC codes are obtained as lifts of small base codes. For example, if you look at 5G standard, you can find that all the LDPC matrices that are used in 5G standard are just obtained from 2 base graphs. Actually, our idea about lifted product codes was, can we also extend this idea to quantum code? So for example, assume we have small quantum code. Can we lift it? So can we assign, can we construct from small tenor graph this large tenor graph? So can we assign these shift values and these group elements to the edges and obtain this larger graph? Unfortunately, it is not so easy to do it in the general case, but the answer is that you can do it if you apply it not to the just every quantum code, but to the code that is obtained using hypergraph product construction. So, and this is the reason why we call this a lifted product, because so we lift the product of 2 classical codes. Let me so briefly describe what is a product of graphs. So the product of graphs is just very natural idea. So you apply the standard product in topological sense, and you can consider graphs as one-dimensional objects, and when you multiply them, you obtain a two-dimensional object, and you can use this multiplication table. And if you ignore all these two-dimensional faces, squares that you have, then you would obtain what is called the Cartesian product. Yeah, and Cartesian product is just a standard graph, it is usually denoted by this box operation. Okay, and what we have for G-lifted products. So G-lifted products actually is very simple idea. So we first lift the first component, then we lift the second component, and after that we obtain the lifted two-dimensional object. So in this lifted two-dimensional object has size G times more vertices, and size G times more edges, and size G times more two-dimensional squares. And here you can consider this multiplication table for this operation. And what is important, this was first noticed by Brookman and Eberhard, that in the case of non-abelian group, so you should multiply from the left for one of the component, and you should multiply from the right. But in the case of abelian groups, you do not have this problem. And this way you obtain this G-lifted product complex. And so in general case, so we can apply, of course, it for any two graphs and obtain this two-dimensional object. And you can also do it for, you can also consider G-lifted analog of the Cartesian product. So in this case, you apply two graphs and you also obtain a graph. So you obtain not a two-dimensional object, you just obtain a graph. And this graph it's also a lifted graph. So it can be considered as a lifted graph. And we call it in our paper G-lifted Cartesian product. Okay, and what is the main idea of our construction? It's very simple. So you have one classical code and you have another classical code, and if you apply this standard tensor product operation, you would obtain what is called hypergraph product code. And in our case, we lift this construction. So we lift this first classical code, we lift second classical code, and we apply this lifted product construction and obtain the graph, which is in fact is a G-Cartesian product, G-lifted Cartesian product of this Tanner graph for this one and for this one. Okay, and you can also describe it in algebraic terms. Okay, so so we have a question: how we can obtain the G-lifted classical code? And in our paper, so we propose to use Tanner codes, which are the codes that are defined on graphs, and bits. So we have bits that are on the edges, and we have checks that are on the vertices, and each vertex, it corresponds to some parity check matrix H, and this parity check matrix, it defines some local code. This is what is called Tanner code. And so we applied for the code that have some symmetry, and this symmetry, by symmetry I mean that they are G-lifted. So it means that we have a free action of group G. And in our particular construction, we use ideas that is similar to the idea of Brookman and Eberhard. So we, instead of just Cayley graph, we use its double cover. And so you can also see how this is can be described as a Tanner graph. So here we have edges that corresponds to bits. So here we have two layers. And here we have parity check matrices. Okay, and But in order this construction to work, we need a graph which is a good expander. And by expander in our last work, we mean a small set expander. So what is a small set expander? Small set expander is it's a graph that expands small sets very well. And in particular, it means that a graph G is called S epsilon small set expander if the number of outgoing edges, the number of edges that goes outside is almost equal to the maximum possible value. Yeah, so in some sense, this is a kind of lossless edge expanders. And sometimes they are even called like that. What is interesting that the good spectral expansion, it also imply this small set edge expansion. So this is quite well known, and this implies that you can use, for example, Cayley expander, such as was used in LPS family, and they are good small set expansion, have this property. So let me briefly say what options we consider. We can consider for the base graph. So we can consider the Cayley graph, which was used in the paper of Brookman and Eberhard. We can also consider, for example, this complete graph. But unfortunately, right now it is not known whether such graphs can whether there are such graphs that are also Ramanujan graphs that have this really good expansion property. And we, in our paper, so we use this bipartite double covers, which are closely related to these Cayley graphs, and they have all the properties we need. So we need a base graph that do not have loops for some technical reasons, and we have a graph that have very good G lifts that are very good expanders, and this graph have all these properties. And actually, this is one of the reasons why we use this. And it's interesting that it's so in theory it is possible to use any small graph as a base graph. And this is a very well-known open problem, whether you can start from constant size base graph and obtain a good spectral expander using lifts. Okay, so to summarize, so our construction is as follows. So we have two Tanner graphs. So here we have vertices, and we have these local codes, local constraints, and we have bits that sit on these edges. And we have two such codes, two such Tanner codes, and we apply this G-lifted product construction to them. And actually we obtain this product, and this product can be also described as some kind of two-dimensional object with which is a generalization of the Tanner graph idea. So here we have three kinds of objects. We have vertices, we have edges, and we also have squares. Yes, and this so actually, and we also have some kind of constraints on each vertex, and this constraint, it's not just classical code, it's a kind of quantum code. So it's so this constraint is actually it's kind of a hypergraph product code, local code. So in some sense, it is really similar to the generalization of this Tanner graph idea. Okay, and here, so I assume that I do not have enough time to say much more, but so here you can see some local view of product of two expander graph, how it looks like. So as you know, each expander locally looks like a tree, and if you apply a product operation to such graphs, then you would obtain something that locally also looks like a product of two trees. And actually the complex that we use, if you look at it locally, so it looks very similar to the product of two trees. But in order to finish our construction, we need also to say how to choose local codes. So unfortunately, the idea that was used in hypergraph construction, where you can just choose a code with good minimum distance and apply this construction and obtain a code with some guaranteed distance. You cannot do this for lifted product and also for balanced product code. So even if you have good minimum distance of component codes, it doesn't imply that you have a good distance of product codes, and that is why so we introduce this property that first look maybe not very natural, but in fact it looks like that are really necessary. And the code, if you choose arbitrarily this local code, that it looks like this construction doesn't work. So it may be that you could obtain codes with just constant minimal distance, not linearly growing minimum distance, just constant minimum distance. That is why it is really important to choose this couple of codes that have this special property that we call product expansion. And in fact, as it turned out, this is roughly equivalent to the robustly testable, well-known property that is studied in by the people who studied locally testable codes. It is called robustly testable, and it is also required that these local codes should have good distance. So let me just briefly say about one of the main ideas in the proof. So it is based on the notion of local minimality. So it's some technical idea, and it's so basically it's just so what we call so the minimum. Let us consider, for example, standard Kitaev toric code. We have minimal code words. So we have code words. A code word is called minimal if you cannot reduce its weight. Yes, and but since you have these local stabilizers, yes, you apply them. You can also ask whether you have whether you can reduce this weight locally by applying local stabilizers, and this way you obtain what is called locally minimal code words. This is a code word that you cannot its weight you cannot reduce locally by applying just individual stabilizers. And this is and you can also consider the weight of the minimal non-zero locally minimal code word, and this is different from the standard notion of the distance. So for example, for toric code, so you also have this locally minimal chain, which is not minimal. So so it's not equal to the standard notion of the minimal distance. And actually our main technical tool is our lemma that in some way it was already proved in these two works. We just combined the ideas and formulated them in a uniform way. So it just states that if you have three-term chain complex, where this local minimum distance grows linearly, you obtain simultaneously locally testable codes, and you obtain simultaneously codes with linear minimum distance. Okay. And this way, so I assume that I do not have time, and let me finish this. And I should say that by applying this lemma and by applying it to our construction, so it is possible to obtain the main result. Actually, our main result is in fact much more general than these two theorems. So it says that if you have a graph with some symmetry.
I'm sorry, but the next session will start.
Okay.
So we should finish. Could you? Should we finish?
Yes, I assume so. Actually, as I said, this is
there is several question on chat box, but we have no time. So please use Q&A Zoom, which will be held after the next session. So thank you for a nice talk.